Hello, my name is Jorinde van de Vis. I'm a postdoc at Daisy in Hamburg, and I'm presenting work that I did in collaboration with Yohei Eme, Ryusuke Jino, and Kazunori Nakayama. And it is about particle production after inflation in models with a curved target space. Reheating is the phase that connects inflationary cosmology to standard hot Big Bang cosmology, which describes the formation of light elements and the formation of the cosmic microwave background. When inflation ends, the inflaton starts to oscillate at the bottom of its potential. And while it oscillates, it transfers its energy into the particles of the standard model. They, in turn, equilibrate and then form a very hot radiation gas. An important motivation to study reheating is that it affects the relation between inflationary parameters and the observables of the cosmic microwave background. This is demonstrated in this plot by the Planck collaboration, which shows the 1 and 2 sigma contours of the primordial tilt and the tensor to scalar ratio, so C and B observables. The colored bands here are inflationary predictions from different models. And the uncertainty is actually given by the uncertainty on the duration of reheating. So if we understand reheating better, we would be able to decrease the uncertainty on these inflationary predictions. Another motivation to study reheating, which is most relevant to this talk, is that sometimes a reheating computation reveals that there's some catastrophe going on your theory. So reheating can then show that your inflationary model is invalid. One example of that is decay of the electric vacuum. So when the quartic coupling of the Higgs field runs negative at large energy, this implies that the electric vacuum is not the true vacuum of the theory. Instead, there is a true vacuum at much larger field values, which is much deeper. Now, if reheating is very efficient and many Higgs particles get produced, the Higgs can actually decay to this true vacuum. And if that happened, we would never have ended up in the universe that we live in today. So this shows that something must be wrong with the theory. Another example is violation of unitarity. It has been shown in the literature already that this occurs in Higgs inflation. Unitarity violation is actually the motivation to study reheating in this talk. But let me make a quick comment, because the unitarity cutoff scale has been a matter of huge debate in the literature in Higgs inflation. And it has been claimed that Higgs inflation is actually not a valid effective field theory. In this talk, I'm putting those issues aside. I'm just going to argue that even if those things wouldn't be an issue, then you still have a problem, a unitarity problem in Higgs inflation, which occurs during reheating. Okay, so what are these curved target spaces? They can occur in low energy descriptions from UV complete theories, for example, supergravity, or when you start in the Jordan frame with multiple fields and non-minimal couplings to gravity. If you then make a conformal transformation to the Einstein frame, you end up with a theory with a curved field space. So this action shows an example. And the relevant thing is this non-trivial field space metric in the kinetic term. So this is not just a delta function. Examples of models with the curved target space are Higgs inflation, α-attractors, and running kinetic inflation. A typical feature of these models is that they have a spiky mass term, usually for the isocurvature perturbation. So these are the modes that are not the inflaton field. And this spiky mass term is generated by the Riemann tensor of the field space metric. And this mass term becomes very large for a very short amount of time, exactly when the inflaton field crosses 0. And typically this leads to very efficient particle production. This brings me to the first part of my talk, in which I will show a semi-analytical computation of the particle number coming from production with spiky mass terms. And I'm focusing on the particle production during the first inflaton oscillation. So this is a sketch of the inflaton field as a function of time after inflation. So inflation ends here, and then I'm demonstrating the amount of production during this first zero crossing. Particle production during reheating can be understood as a mixing of positive and negative frequency modes. And this is described by the evolution of the Bogoliubov coefficients, alpha and beta. And the label K here denotes the momentum. So these are the evolution equations of alpha and beta. And in principle, you would have to solve this coupled system of differential equations. The initial condition is alpha equals 1 and beta equals 0. And then later on, the particle number is given by the absolute value of beta squared. Now things can be simplified a lot if you use the so-called Born approximation. And this assumes that alpha equals 1 and beta is small. And in this case, you can just integrate the equation for beta to obtain the particle number. We will use this in our approach, but we do a trick. Since we are only interested in this part of the evolution, we can actually use a change of variables and replace the integration over t by an integration over phi, the value of the inflaton field. The particle number is then given by this formula. We then take the limit of capital phi, which is the end point of the oscillation, to infinity. And if we do that, we can use Cauchy's residue formula, which tells us that the particle number is just the sum over the residues of this function here. And that can be straightforwardly computed. So I'll now show two examples where we did this. The first is isocurvature mode with a mass with a single pole, as is shown here. And on the right, I show the spectrum. So it's the particle number f as a function of k, the wave number. In solid, I show the solution to the numerical solution to the mode equation. And in dashed, I show the result from the semi-analytical approximation. And you see that they match very, very well. The second example is a mass with a double pole, as demonstrated here. Again, the dashed line shows the semi-analytical approximation, and the solid line shows the solution, the numerical solution to the mode equations. In this case, again, there's a very good overlap between the two for the large momenta, but for smaller momenta, there's actually a discrepancy. The reason for this is this term here. So this term actually gives you another resonance, another source of resonance, which is not related to the spike. And this is, of course, not accounted for in our semi-analytical formula, but it does lead to particle production. Another interesting feature in this double pole situation that I would like to point out are these oscillations. And they are caused by an interference between the contributions of the different poles. And it's actually very interesting that this is both captured by the numerical solution as well as by the semi-analytical approach. Now, what are the limitations of our semi-analytical approximation? First of all, we use the Born approximation, which assumes that particle number is small. Now, this sounds very maybe inappropriate, but actually in the case of spiky masses for curved target spaces, this limit is not that bad because spiky masses typically lead to particle production with very high momentum, but not necessarily large occupation numbers. But it does limit our approach to such situations. So, for example, a narrow or broad resonance does not apply. This Born approximation does not apply. Secondly, we assumed that the endpoint can be taken to infinity. And this is only valid if particle production takes place far away from the endpoints. And third, as we saw in the double pole case, there could be other resonances due to narrow or broad resonance, and these are of course not taken into account in the semi-analytic approximation. All right, now we're going to look at some particle production in specific inflationary models, and let's see how well our semi-analytical approximation is performing. The first example is running kinetic inflation. The inflaton field is phi here, and the isocurvature field is chi. And as you can see, there's a non-trivial field space metric. The spike mass of the chi particle is given here, so it's very close to the single pole mass that we saw already in the examples. Now, in this plot, we show the energy density in the chi mode after the first inflaton of zero crossing as a function of the cutoff, as a function of the momentum, but we have rescaled the momentum by the cutoff. Now, unitarity is violated if the maximum of the momentum lies beyond the cutoff scale. Our graph shows us the result from the semi-analytic approximation in dashed and the numerical solution to the mode equations in solid. And you can see that they are corresponding to each other very well. There's only a small discrepancy. You can also notice that unitarity is actually violated in both of these cases because the maximum momentum lies beyond the cutoff scale. As far as we know, this is the first time that unitarity violation has been pointed out in running kinetic inflation. The second example is Higgs inflation. I'm showing here the action in the Jordan frame. Actually, it's a little bit modified from Higgs inflation because I'm only taking one Goldstone mode, chi, and I take the non-minimal coupling of the phi field, which is the Higgs field, the inflaton, and the chi field to be not exactly or not necessarily the same, which is a slight generalization of Higgs inflation. Both of these arguments do not, both of these factors do not really matter for the main argument that I'm making. So in this case, the spike mass resembles the double pole case, as you can see here. Again, we show the energy density in the chi field, the Goldstone mode field, as a function of the momentum. And again, I've rescaled by the unitarity cutoff scale, which is given by the Planck mass over xi. Dashed shows the semi-analytical approximation and solid the numerical solution. Again, there's quite a good overlap between the two. And as you might notice, again, unitarity is violated, as we already knew from the literature. And unitarity violation happens for large values of the non-minimal coupling psi. Okay, what about Palatini Higgs inflation and α-attractors? These are also models with a curved target space. But it has been demonstrated in literature that during reheating, unitarity is actually not violated. So now you might wonder, what decides whether unitarity gets violated during reheating or not? It turns out that there's actually a very simple argument to see whether unitarity is violated. So let's say that lambda is the typical mass scale of the curved target space. It turns out that this scale coincides with the unitarity cutoff of the theory. Now, when the inflaton crosses zero, particles are produced from the spiky mass term, and the typical momentum of the produced particles is given by the velocity of the inflaton field divided by the cutoff. Then from momentum conservation, the velocity of the field can be related to the inflaton potential at the end of inflation. And of course, as I just said, unitarity is violated when the maximum value of the momentum exceeds the cutoff scale. And this gives us the following very simple condition for unitarity violation. So when the inflaton potential at the end of inflation is larger than the cutoff scale to the fourth, we expect unitarity to be violated. And this condition is satisfied for Higgs inflation and for running kinetic inflation, but it is not for Palatini Higgs inflation and α-attractors. So this explains why unitarity is violated in the first two models, but not in the latter two. This brings me to my summary. So I've shown that there are models with a curved target space, and they typically have a spiky mass term for the isocurvature mode, which leads to very efficient reheating. I've then demonstrated a semi-analytic approximation for the particle number after the first zero crossing, which turned out to be a very good description of the particle number. Then I demonstrated that running kinetic inflation and Higgs inflation have a violation of unitarity for certain choices of the parameters, but Palatini Higgs inflation and α-attractor do not show any violation of unitarity. It turns out that there's actually a very simple condition for unitarity violation, which is that the potential at the end of inflation should be larger than the cutoff to the fourth. And this determines whether unitarity is violated or not. Thank you very much for your attention.